Let's take a look at an example of using our Widlar current source. So as with all the examples in this class, I would encourage you to maybe pause the video and try to work through this on your own, and then come back and watch the video to check your steps and make sure everything looks good. And of course, at any point, if you have questions, feel free to let me know. Okay, so for this example, I've copied our Widlar circuit here, and what we want to do is we want to determine the values of R1 and RE such that we have a reference current of 1 milliamp and an output current of 12 microamps. And we're also told to assume that VBE1 is 0.7 volts. And I've also updated in our circuit compared to the last time we saw it. Notice we're given our voltages V plus and V minus as 5 and negative 5 volts respectively. One thing to note too, for instance, if you were to see this on a test or in homework, and you're just told to create a circuit with these conditions here, and you weren't necessarily told what type of circuit to use, the fact that our IREF and our I naught are different, and they're this different, is pretty much a dead giveaway that we're going to be talking about a Widlar current source. Okay, so let's get into how we solve this. So the first thing we're going to do, we actually did not talk about when we looked at our Widlar current source, and that is how we would solve for our R1 to get a certain IREF, or if we would calculate our IREF for a given R1, and that's because it's the same as what we saw for a 2-transistor current source. So essentially we're just going to do KVL along this path here, and doing KVL along that path, what we're going to see is we have V plus minus V minus is equal to IREF times R1 plus VBE1. So written a little different than what we've seen before, but of course the same thing. We've just got that V minus on the other side. So if we solve this for, in this case, we know IREF, we're told that's 1 milliamp, and we're solving for R1, we can do that pretty easily. We can say R1 is then going to be equal to V plus minus V minus minus VBE1 divided by our IREF. Okay, so now we just plug in our values. So we have 5 volts minus a negative 5 volts minus 0.7 volts. And all of that is divided by our IREF, which is 1 milliamp. And so if we plug that into our calculator, we get 9.3 k ohms. So that's our value for R1. So now if we want to solve for the value of RE, what we're going to do is we're going to use that equation from our Widlar current source. And so if we rearrange that equation to solve for RE, we have that RE is equal to VT divided by I naught times the natural log of IREF over I naught. So we've essentially just moved that I naught over to the right side. So now we plug in our values. So remember, our VT is our thermal voltage, which is equal to KT over Q. Oftentimes you don't need to actually calculate that. If we assume room temperature, that's about 26 millivolts. And so that's something good to know, for example, for the FE, you might see that. Our output current is 0.012 milliamps, or 12 microamps. And so I'm just going to keep everything in milliamps so that I don't have any issues with my units. So I'm going to have then log of our reference current, which is 1 milliamp, and our output current is 12 microamps, which I'm going to write as 0.012 milliamps. So of course, if you're uncomfortable with units, what I would always recommend is just going back to your base of volts, amps, and ohms. So if we plug this in, we get our RE is approximately 9.58 k ohms. Okay, and so you might be saying, well, I thought our resistor values are going to be small. And so actually this is relatively small considering we're getting an output on the order of microamps. So if we think back to, let's just say our 2-transistor current source, because that's the easiest to adjust this to, we wouldn't have our RE, and our output current, I out, would be approximately the same as our IREF. So now if we wanted our output current to be our 12 microamps, what we would have to do is we would have to update this value to be approximately 12 microamps. So if we come in here, and now instead of milliamps, we have microamps, we've added a factor of 10 to the minus 3 to the denominator, which in our answer over here is going to add a factor of 10 to the 3. So we've essentially reduced this by roughly 1,000 times, this resistor size for RE, by using our Widlar source example, or our Widlar source configuration, as compared to another configuration. Okay, so that's sort of the easy way to do this if we're asked to solve for these resistors. And one thing I want to note before we look at if we want to solve for I naught. So let's first just note the difference for our base emitter voltages. So our VBE1 minus VBE2, we know is approximately equal to I naught times RE. So that was something that we found as we were doing our derivation, and we know that just comes from a KVL around this bottom loop here. Okay, so if we plug in our known values then, now that we have our RE value, we can say this was 12 microamps for our output, so 12 times 10 to the minus 6, and this is 9.58 times 10 to the third. So again, if this is what I'm recommending, I've gone back to my amps and my ohms just to make sure I've not made any mistakes. If I plug that in, I see that is 0.011, sorry, I've got an extra 0 in here, 0.115 volts. And so what that means is that our VBE2 is approximately equal to 0.585, because remember we were told that our VBE1 is 0.7. And so the reason I do that is I want you to notice that even a relatively small difference in these VBE values can result in large differences between Iref and our output current I naught. So just something to keep in mind. Okay, so that was what I would consider a relatively straightforward Widlar example. But let's say for our Widlar circuit, instead we know all the values except for our I out. So let's see if we can just copy this circuit here, and let's get rid of some of these things that we're not using anymore. Okay. All right, so that should be about good. So now what we're saying is, let's say we still have this is 5 volts, we still have our V minus is 5 volts. We're still told that this VBE1 is about 0.7 volts, and we're told that our R1 is equal to 7K ohms, and our RE is equal to 4K ohms. And so what we want to find is our output current, so, and our reference current. So what is our Iref and what is our output? So our Iref is going to be pretty straightforward using that equation that we saw earlier for the previous part of our example. We're just going to swap our Iref and our R1. So in this equation here, we're just going to move our I1 to the denominator and bring our Iref to the left side. So doing that, we can see that our Iref is just going to be equal to our V plus minus VBE1 minus V minus divided by R1, which is equal to 5 minus 0.7 minus negative 5 divided by, and then our R1 was given as 7K ohms now. And so we get that our Iref is approximately 1.33 milliamps. So pretty straightforward still to get our Iref. So it gets a little trickier when we try to find our I naught. So going back to our Widlar equation, we plug in for our RE, we have that is 4,000 ohms. Our I naught, we don't know, and that's equal to our VT, which assuming room temperature is about 26 millivolts or 0.026 volts, times the natural log. Now we just found our Iref was 1.33 times 10 to the minus third amps, and we don't know our I naught. So now we're running into this problem where we have this transcendental equation. Okay, so transcendental equation. And so as we've talked about earlier, this is either going to require iteration, if you're doing this by hand, or some type of computer. So you can use Excel, MATLAB, Octave, any of these types of programs will help you do this. But say, and I doubt you would see this, but say you run into something like this on the FE. Well, what you could do in terms of iteration is you could basically just guess and check. So for instance, we could try some value. So let's say we try I naught is equal to 100 micrograms, because maybe that, for whatever reason, seems like a reasonable value. So what that's going to result in is on the left side of our equation we have 0.4, and on the right side of our equation we have 0.0673. So obviously that's not true. So what we would say is we can play around the values if it's not obvious right away, but it turns out that our I naught is going to be too big in this case. So we say, all right, well, let's try something much smaller. And so the idea here is sort of like artillery, right? You're kind of going to hone in on the answer. You want to overshoot both ways and then kind of hone in. So now we get 0.004 on our left side if we do I naught equals 1 microamp. And we get that that's equal to 0.187 plugging in 1 microamp to our right side. So obviously that's not true either. And now we've gone too small. Okay, so maybe we split the difference. So let's say maybe we try going 50 microamps. Okay, so if we go 50 microamps, now on our left side we have 0.2, and on our right side we have 0.0853. So again, that's not equal. We know we've gone too big again. So we know now it's somewhere between 50 microamps and 1 microamp. So you can kind of see where this process is. So maybe we split the difference again, and we say, well, let's try I naught equals 25 microamps. And so that's going to give us 0.1 is equal to 0.1033. So that's not quite equal, but you can see now we're getting a lot closer, and maybe in some cases that is close enough if we're just doing 1 or 2 sig figs. But we could say maybe this is barely too small. And so maybe we could increase that a little bit. So maybe we go up to 26 microamps. And then we say we get 0.104 on the left side and 0.102 on the right side. And again, that's close, but not quite. So depending on the accuracy we want, we could either say that's right, or we could maybe say now this is barely too big. So looking at that, we could know that this is somewhere between 25 and 26 microamps. So 25 and 26 microamps. And in most applications, and certainly for this class, that would be more than enough. But like I mentioned earlier, we can solve easier using MATLAB, Octave, Excel, or some other program like that.